Hi. Can anyone hear me? If you can hear me, can you type a yes in the comments, the chat? Okay. Um, Hi. So that works well, huh? Okay. So I just want to say that there might be like a 5 second latency, like delay. So please be aware of that. And just if you have any questions, you can leave your comments here, like in the chat, or you can just say that I have a question. So I will stop it and I can answer your question for like some of the slides here. I'm very sorry that not using the WebEx. There's just like two concerns. Why? One is that the WebEx doesn't have like a good connection, like network connection, and also like I'm not so sure if I can record it and upload the full video online. But the YouTube, with YouTube, I can just directly post the video online, so anyone can see that. So and I think like WebEx has like limits, like upload limits for uh, for uploading a video or something. So that's why I'm choosing the YouTube right here. Um, okay, so I think everyone already get the email for the homework. I think it's homework 4. For homework 4, you just need to conduct the analysis. Basically, just calculate things on by the table. So there's a table also uploaded in the folder. So everything will come from the table. Um, so you don't have to use the R because basically you're just gonna like write down some hypotheses and then just calculate based on the table. Um, if you have any questions for the homework, just let me know. And uh, okay, so let me see how many people we have here. Okay, so for today, we're just going to talk about the transformations of variables. Uh, I think everyone can see this. So we will go like back and forth between the slides and the R code. But I think for today, like basically all the R code is based on the R code we talked about before. So it's based on the regression diagnosis and also the just the summary of the linear model. So it will not be that hard for you guys. Okay, so why do we transform the variable? So it's because like the associations between predictors and outcome may not be linear, and the transformation of variables can help us to just simplify the relationship, and more importantly, it will normalize the residuals, like stabilize the residuals, um, and also eliminate the heteroscedasticity. So in the book, it's talking about like especially like the transformation can help us uh, to um, to alleviate the problem of linearity, um, normality, and also the violation of homoscedasticity of residuals. And there are two things to notice here. First is that we are transforming variables and representing the relationship in a linear model. So for some nonlinear models, it is hard for us to transform back into like a linear function. Um, The second point is that when any transformations to variables is applied, we need to recheck every assumption for regression to see if some of the problems have been solved. You will see that today. Okay, so next, um, how do we transform variables? So there are a lot of ways to transform variables, but mm, here there are some situations you can get reference. So the first situation is that if you have a very strong theoretical model, like today's example, later on you can see that today's example. So if you have a very strong theoretical model, you need to transform the variables in accordance with the model. So for example, like we're going to use the exponential model for the bacteria today. So the bacteria example is using the exponential model, and we're going to do the transformation of the variables according to this model to make it like a linear model. And in some other cases, it's like the Fechner's psychological law. So that will have like a logic model there. So um, this is when you have a very strong theoretical model. You need to transform with accordance. Okay. And then the next is if you have a weak theoretical model, you can just transform the variables to see if the transformation helps to stabilize the residuals. Okay. Um, and basically, I think like for most of the time, you might not have like a very strong uh, theory to back up your rationale of transformation. But still, like transformation can help you to avoid a lot of the problems in residuals and and in the relationship, the linear relationship. So you could try the transformation, but there's no like a general rule, like a very strict rule. It's just like a sort of like a very subjective rule or rule of thumb. So you could follow that, but just be careful that there's in such case you don't have a very strong theoretical base. So that rule is called Belgian rule, and that is represented in a graph. So let's just look at the graph here. Okay, so let me explain this graph. It's pretty straightforward. So as you can see here, there are four segments of uh, the line to represent this like a whole circle here. So let's just take one segment as an example. So if the relationship between x and y is uh, better to be represented like in this kind of shape. So like this part. So in that case, you can either increase the x to become like a power term, like a power of 2, power of 3, or you can try to increase y. You can just use like y squared or y cubic. So that's the general rule. If you see the relationship is between x and y like this, okay. So same thing will apply to here, here, and here. So if you can see that the relationship between x and y is like this, you can either decrease x or increase y. So in this case, you can see like you can use the ln to x, which is the natural log, and the square root of x, and 1 to x. Okay, so this is something you can do when you see here. And here is just when you see the relationship is like this, you can decrease x or decrease y. And if it's like this, you can decrease y or increase x. So that's pretty straightforward, but this is not theoretical based. So just be careful about that. Okay. So here is just a review for the regression diagnosis. So we have a lot of assumptions to check, right? So transformation is especially helpful to alleviate some of the assumptions, some of the violations of the assumptions. So, mm, so for missing data and outliers, and also the independent error assumption, I think the transformation will not help that much. But transformation can help us uh, to represent the relationship between variables in a linear way, and also it will normalize the residuals and make the residuals homoscedastic. And here we are going to focus on these three, these highlighted ones, later on in our example. I believe that you already know how to check the violation of assumptions based on the homework and also the lecture. So let's just go straight forward to our example here. Okay, so for today's example, we're going to use the bacteria data in the textbook. You can just download the data set from the Blackboard. And actually, also you can find every data set we're going to use in this semester, like by this website. So you can just click on it. You will see a lot of the data set. Okay, so in this data set, there are two variables here. So the first one is just the number of surviving bacteria in 100 seconds, and T means the time units. So in this case, the NT here is the dependent variable, our outcome, and the T is the time units, is our independent variable. So based on the theory, you can see here, this is the model to represent the relationship between the time unit and the number of surviving bacteria. So you can see it here is an exponential model. And N0 is the number of bacteria at the start of the experiment. And the beta 1 is the decay rate, is the destruction rate. So just remember this model, okay? So, however, if you plot the relationship here between T and the NT, you can see that the line is better represented by a curve, right, than the blue line here. Well, for sure you can just use the blue line, but as you can see here, it's clearly like a curvy linear relationship between the T and NT here. And here is just talking about the relationship, so we can just skip this part. Okay, so this is the relationship in the original data. Okay, so before the transformation, actually we're just going to naively fit the linear regression line to the data. So this is the model you see in the past, right? This is just a simple regression with the intercept and the slope, right? You fit the line, like the straight line here, like the blue line here, into the data, right? So let's see what will happen. Okay, so here our model actually kind of significant, right? So our F test is significant. So it means that the predictor significantly predict the outcome. And our R square is 0.82, which is like 82% of variance is explained by this independent variable. So looks we are good, right? However, it's kind of so let's see. Let's check the assumptions first and see if we have a very good model here. Okay, so based on the model model fit indices, there's not many things we can tell, right? Okay, so actually I will go through the code later. So for the code, there will be like just actually just two part before the transformation, which is like here, and after the transformation. So first, we can just like we are just going to see the regression diagnosis, or the plots, right? The plots first, and then we'll go through the codes for the here, and then we're going to do the transformation and go through the plots, and we're going to go back to the code. And I don't think the code is that complicated, and the code is corresponds to every slides here, so you don't have to worry too much. Okay, so here we're just going to skip the missing data and also the outliers check, because those two because the transformation will not help those two. You know, like for the missing data, you can do the missing data treatment, and also for the outliers, you can detect the outliers and do something with the outliers, but the transformation might not help that much. Okay, so first we're just going to check the linearity of the relationship. As we checked earlier, like here, it is better represented by this red line than this blue line. And also you can see that in the residual plot. So on the x-axis, it will be standardized predictive value. So this is a predicted y. Is a y value here, a y hat value, and it is standardized. And here is a standardized residual. And as you can see here, this is not linear. And clearly there's like a pattern or something here, right? So and also like so this is I put a reference line here. This is 0, and you can see here there's like this is like an outlier, but and based on the residual plot, the residuals should be like randomly scattered around this reference line here, right? So in this case, we do not have like a linear relationship here between the the predictor and the outcome. So this is problematic. Okay. Next, we're going to check the normality of residuals. There are a lot of ways to check that, and basically we're just gonna visualize that by the histogram and also the QQ plot. Here you can see that it is the residuals are positively skewed because the outliers on the positive side. So we have a kind of severe skewness, right? Positive skewness. Here, and also you can see here, right? On the like this corresponds to here, right? So here you can see the skewness also, because this is the reference line, and our dots are going that way. Okay, so we kind of violate the normality assumption here. Next, for the homostaticity of residuals, as you all know, that this is the predictor versus standardized residual. This is the standardized y hat value versus the standardized residual. So those two will look a little bit similar, right? The relationship, you can see there's like a curve here, like similar curve from like here and also here. So this uh, indicates a little bit like the problem of heteroscedasticity, but due to our sample size, I think we only have like 15 observations, so it is difficult to determine if we have like a homoscedasticity violation, right? So I think, well, I already know the answer. So like later on, we'll see that actually our residual plot will look much better than here. Okay, look much better. So we'll go through that later. So next, so for the independence of residuals, so for this one, independence residuals is not very common in the non-time series problems. So I think there are some there could be situations where like the residuals are not independent to each other in the in the non-time series situations. But I think I have like a notes here. You can see that. So for the independence of errors, it's potentially very serious in the time series regression models, but the independence can also be violated in non-time series models if errors tend always have the same sign under particular conditions. So this will not be the situation here because we have positive and negative. However, for the time series model, the independence of residuals, this violation can be addressed by the autoregressive model. So just keep that in mind, and that might help the violation of independence of residuals better than just transform the variables. But we'll see that later to see if we have solved that problem based on the transformation. But usually you need to use another way to address this problem. Okay, so before the transformation, we are going to see the code. Okay. Oh, by the way, can you see the screen clearly, or here, because I'm going to show you the code, so it might be very small. Let me see if I can make it like larger. Okay, so okay, cool. Sure. Okay, so this will be a little bit larger than. Okay. So as usual, we're going to load our data set. Okay, so and we can examine our data set. So here we have two variables here. Okay, so t and nt as we talk about that. Okay, thank you guys. Yeah. Okay, so here we generate the scatter plot, and we want to see the linear line and the curvilinear line. Okay, so you can see here, and we are going to fit the simple regression to our data, and call the model the model summary. Okay, so that's very simple. And here we're going to just generate the what we want is the standardized y hat and also the standardized residual. So we only need those two. Sometimes it will be better if you just like put those two variables, um, add those two variables into the data set here. Um, I'm just too lazy, so I didn't add them into the data set. You could do that, by just calling like, for example, just saying df dollar sign y hat, and just give the value y hat. So if you like run that, you will generate the one column of the variable called y hat in the data set here. Okay, um, but I'm just too lazy, so I don't want to do that. So you can see here we generate the standardized y hat and a standardized residual. Those are the two things we want. Okay, and here this is checking the assumption of the linear relationship. Okay, this is just a residual plot. So this standardized y hat against the standardized residual. And the next is just the normality of residuals. We have two ways. The first way is the QQ plot, and the second way is the histogram. Okay. And the third is the homoscedasticity of residuals. And you can see here, this is just a predictor versus the residuals, right? And you can, and we have another one which you already generated, which is the standardized y hat versus residuals. You can also use that for examining the homoscedasticity. And then the last part is the independence of residuals, which we use the 1 to the number of row in the data frame. So it's 1 to 15. So we have 15 observations. So here is just generate the index for the observations, and you can see here this is our residual. Okay, so that's it for the everything before the transformation. Okay. Okay, so next. Okay, so as we mentioned before, right? So this is our theoretical model here. However, this model is not a linear model. So what we can do is that we can transform the variables here to make it into a linear model. We're going to represent the relationship between the predictor and the outcome in a linear way. So actually, we're going to take the log of both sides. So in this case, as you can see here, our y value becomes the log of the original data nt. So, and also on the right side, this is the initial number of bacteria. So this becomes the log of the n0, and we have the beta 1 here, and times our predictor. So you can see here this become an additive model here. So this is in our intercept, and this is our slope, right? So our beta 0, which is our intercept, becomes the log of the n0, and the outcome becomes the log of the nt. So here we successfully transform the variable and make the model into a linear model here. So here, if we just introduce the error term, so we can form our linear model with our transformed y here. So you can see here, this is our model. So basically, we're just gonna take the log of the y, and then generate the linear model based on our transformed y and the predictor t. Okay, so let's do that in the R. So that's very simple. So log and the variable here will generate the natural log of the variable. So by default, R will give you the natural log. But if you want to use the other base, you can just use the base argument, like comma base equal to 10 or to 2 or something like that. Okay. So we're just gonna use the default because that's what theory suggests, and we are going to just generate the log of the y here in our data set. So you can see here we have a new column generated, which is the log of the nt. And now, as you can see here, this is the scatter plot between the our predictor and the y. Okay, so you can see it's clearly it's a linear relationship between the two here. Okay, so we're going to conduct the regression analysis. So we fit the linear model between the predictor and the log y, and you can see here we have a much better result, and we have a higher R square, and actually we have a higher F value, and we have a more significant, not more significant, but like a larger T value for the predictors compared to the slide 9. Okay, you can just compare to slide 9 here. Let me see. Okay, so here is like the model before. So we only have like 0.82 R square, and our F test value is just 60. But here you can see here we have a F value, a very large F value, and we have like 98% of the variance explained by T already. So it's pretty good. Okay, and here you can see our estimate here. That this estimate is the beta 1, right? The beta 1 hat. So this is the beta 1 hat here, okay, for the predictor T, and this is the estimate for the intercept, which is log nt. Okay, so our beta 0 estimate is 5.97, and the beta 1 estimate is the negative 0.22. Okay, so this is our model. Okay, so as we said, the original model is in an exponential model, so we need to transform back for the intercept back into the n0. What we get here is log n, right? The estimate of log n0. So this estimate here is actually log n0 hat, right? So we need to transform this back into the exponential form. So in that case, e to the 5.97 here will equal to 392.68. Okay, so this is our estimate of the n0. However, based on the textbook, this estimate of the n0 is biased. I don't think the textbook talked too much about it, like why it is biased, but so far we're just gonna say that it is biased and it needs to be corrected. So this will not be very common. You transform like the variable, like the unbiased. So here the log of the n0 is unbiased. But if you transform back into like the exponential, it will be biased. So this will not be very common, but it is the case here. So we're going to do some correction to this transformation. So here, as you can see, we're just going to minus the half of the variance of the beta 0. So in this case, the n0 will be adjusted to be lower. Okay, so it will be 391.98. So our estimate of the n0 based on the log of n0 here is 391.98. And we're just gonna put it here. And our beta 1 estimate is negative 0.28, right? Negative 0.218. So we're gonna put it here. So this is our beta 1 itself. So here we get the estimated model here. Okay. This is the final equation for the theoretical model. Okay. So after that, we can just see if we successfully did the transformation. Oh, actually, I think I made a mistake here. So this might not be the correct plot. So this is not the correct residual plot, but I think it will be the correct one in our code. So let's just generate that correct residual plot. So as you can see here in the code, we're just gonna just run this code. This is just the log y, and this is the predictor, and this is the summary of the transformed model. And here we generate the standardized y hat and the standardized residuals. To separate those from the original ones, I renamed everyone. So I renamed everything here. So it will be residual standard residual dot t. So you can see everything dot t will be the values for the second model. Okay, and this one will be the correct residual plot. Okay, so this one should be the correct one. So let me change that. So let me just go here to delete this and put it here. Yep. Copy image. Oh. Can I do that, or should I save image as? Let me use this one. Let me just save this image. Okay, so let me delete this one and put the correct residual plot, and I will upload the correct PowerPoint. Let me just add this picture in here. Okay. So here, this one is the correct one. Okay, so this is our standardized y hat. Here is a standardized residual, and you can see clearly compared to the previous one, the residuals are pretty much randomly scattered around 0, right? Like up and down, like without any kind of pattern or something. So in this case, we are good. It is actually really good here. This represents that we have like a linear relationship between the x and y. Okay. Next, for the normality of residuals, as you can see here, we approach normality of residuals. So the distribution approaches to normal. Right here, you can also see we have a little bit violations, but those are actually kind of small. So pretty much we're okay for the normality assumption. Well, we have very few observations, so that's why the dots are not it's just like 15 dots here, so it's hard to look at. But you can see that like this is for the central tendency and the variability, we're kind of good, not so much. We don't violate the normality that much. Okay, Uh, let me see. I think those two are not correct either. Let's just go to our R code and let's see if we can generate the correct ones. Actually, the normalities are good because this one is the correct one, and also this one uh, is also the correct one. And let me see if the yeah, okay, this one is the correct one. Okay, and let me just generate those two. Okay, let me change here. This is not correct. Where did I put that? Oh, downloads. Okay. I don't know why. Like, well, yesterday I already put those things on it, but it just magically disappeared, and it just is still like the old ones. I don't know why it happened. Maybe it's just like the Google Drive didn't save the latest version. But I mean, I would. Well, it's there's no much trouble. It's just I'm just gonna change it now. So okay, so and also the last one. Oh, but this is the last one. Sorry. Okay. So here, this one. Yeah. Okay. So um, these two are the correct ones. So when we check the assumption for the homostaticity of residuals, the first one is the predictor versus the standardized residual, right? And you can see here it's also scattered around. It's very similar to the standardized y hat versus the standardized residual, right? Those two should be like similar here. And those are, you can see the residuals are randomly scattered around zero. So we are good here. It looks very good. And also here, this is the residual versus the index. And then also you can see here, based on the index, you don't see anything here. You don't see a uh, uh, any dependence um, with the residual of each other. So it is randomly scattered. So in this case, the transformation help us a lot. Transformation help us to solve a lot of the problems of the linearity, the homostaticity, the normality of residuals, and it also help us to solve the independence of residual. But as I said, because those independence of residual problems will happen most likely in the time series, and we don't have to care about that too much about the dependence of residuals right now. So and let's just go through quickly go through the code. As I said, we generate the model with the transformed outcome and the predictor, and then we call out the model summary. And here we generate the standardized predicted values and the standardized residuals, and we plot them. And so to check every single assumptions, uh, and that's it for the code. Uh, Any questions so far? Um, so I just want to mention again for those coming a little bit late. So for the homework, you don't have to use the R, and you don't have to use the APA style actually. For this code, you just have to follow the questions and answer the question accordingly. Like if the question asks you to do the hypothesis testing, or it's just basically just state the null hypothesis and the alternative hypothesis, and then just use the correct formula to calculate the incremental R square or something like that. So just be careful about that part. And um, the due date is I think it's after spring break, is the Monday, 23rd. Yeah, 23rd. 11:59 p.m. So 11:59 p.m. on March the 23rd. And I believe that there will be another homework right after that, because Dr. Kim already talked about the transformation of variables. So um, you guys need to prepare for that, because we are like 1 week after, like, so sort of like we're behind the schedule for the homework. So yeah, and also like for the for this homework, there will be like 2 extra credit questions. You don't have to worry about those if you don't want to do that, but feel free to do those too. It's not that hard. It's just the follow-up questions in the textbook. So you should be able to answer them like without any problem. So just try it, and that's it for today. Let me know if you feel like this is a good way uh, to having the lab. Like, do you want to keep this format, or you want to change to like WebEx based on your experience? Just let me know. Okay, so if you think this is okay, also just let me know if you think we can just continue to use YouTube stream. Okay. Okay, so thank you guys so much, and see you guys after spring break online.